Hello and welcome back to another Orange Coast College Mathematics video. In this video we're going to talk about solving systems of two equations. Now, what exactly is a system of two equations? As the name suggests, there are two equations, and the system just means that they're kind of paired together. Now, what does it mean to solve a system of two equations? Well, it just means that I want to find an x value and a y value such that both of my equations are true at the same time. If I can find such values for x and y, then we have a solution to our system. So there are two ways of solving our system. Our first method is going to be the substitution method. And this method says that we're going to take one of our equations and solve it for one of our variables. So I'm going to get y equals something, or I'm going to get x equals something. Once I have that, I can then substitute that into my second equation, and then I'll be able to find out a value for one of my variables. As in, x will be equal to 3 or 5 or some number. And then, now that I know what x is equal to, I can plug that back into either of the equations that I have before, and I'll be able to figure out what the other variable is. So, let's go ahead and try the substitution method out on number 1. So number 1, we've got a system of two equations. We have y minus x is equal to negative 5, and we have 2x minus 5y is equal to 1. So, following our substitution method, I'm going to take one of these equations and I'm going to solve it for one of the variables. Now, I think this top equation looks easy to do because it's y minus x is equal to negative 5. So all I really have to do to get one of the variables alone is add or subtract the other one over. So I'm going to go ahead and take the top equation and I'm going to isolate y, as in I'm going to have y equals stuff. How do I do that? I'm just going to add x to both sides. So I'm going to go ahead and rewrite it. So we have y minus x is equal to negative 5. Now I want to get one of the variables by itself, so like I said, I'm going to add x to both sides, and this will become y is equal to x minus 5. So now that I've solved for one of my variables, I can take that and substitute it into the other equation itself. So my other equation is 2x minus 5y is equal to 1. But we just found out that y is equal to x minus 5. So this will be 2x minus 5 times x minus 5 is equal to 1. Solving this out, we're going to have 2x minus 5x plus 25 is equal to 1. Combining our x terms and subtracting 25 over, we're going to have negative 3x is equal to 1 minus 25, so negative 24. Now dividing both sides by negative 3, we'll have x is equal to positive 8. Okay, so we have a value for x, but now I want to know what y is equal to. So I can take this x and I can plug it in to either one of these equations, and this should give me a value for y. So let's go ahead and do that. Since I'm allowed to use either equation, I'm going to use the top one because it looks easier. So we're going to have y minus 8 is equal to negative 5. So I'm going to add the 8 over, and my y is going to be equal to positive 3. So the solution to my system of equations is going to be 8, 3. However, we should actually check that this works for both of our equations. So let's go ahead and try it out. Let's do the top one in red. So we'll do y minus x is equal to negative 5, and we'll substitute the 3 and the 8 in there. So we have 3 minus 8 is equal to negative 5. 3 minus 8 is negative 5. So negative 5 is equal to negative 5. That's a true statement. Now let's check the other equation. We have 2x minus 5y is equal to 1. So 2 times 8 minus 5 times 3 is equal to 1. 2 times 8 is 16. Minus 5 times 3 is 15. Is equal to 1. 16 minus 15 is equal to 1. And so we have 1 is equal to 1. That is also a true statement. So our solution of 8, 3 works for both of our equations, meaning that this really is the solution to our system. Moving on, there's another way of solving our system of equations, and it's called the addition method. Now, in order to do this, we want to get both of our equations in the ax plus by is equal to c form. From there, we're going to create opposite coefficients for one of the variables. And what I mean by that is, if I have a negative 5x in one of my equations, I want the other one to have a positive 5x. I'm going to do that by multiplying or dividing my equation by some number to match those up. Once I have that, I'm going to add my two equations together. And so, if I add these two quantities together, what's going to happen? My x's will disappear, and I'll just be left with a bunch of y's, or whatever other variable that we have. Then, I can solve for what y is equal to. Then we'll take the variable we just found, and we'll plug it in to find the value of the other one. Then we can check our solution to make sure that it satisfies both of our equations. Okay, so let's try to do this with number 2. So let's check out our coefficients on our x's and y's just right away to see if there's a variable we should try to eliminate before the other one. Now, there's no rule saying that you have to eliminate your x's or you have to eliminate your y's. It's just going to be a matter of personal preference. So, in the case of number 2, I see that our x has a 3 and a 2. Now, they're not multiples of each other, so I'm going to have to multiply both equations by some number in order to get them to have opposite coefficients. But if I check out the y's, I have a positive 1 and a negative 3. To get these to have opposite coefficients, all I have to do is multiply one equation by one number instead of multiplying both equations by a number. So I'm going to try to eliminate the y's in this case. So I have 3x plus y is equal to negative 7, and then I have 2x minus 3y is equal to negative 1. Now, as long as I do the same thing to both sides, it's a legal move. So I'm going to multiply both sides of the top equation by 3. Once I do this, we're going to have 9x plus 3y is equal to negative 21. And then we'll have 2x minus 3y is equal to negative 1. Now, the next step would be to add both of these equations together. However, a lot of people don't necessarily find that intuitive, so let's check it out at a little bit slower pace. If I take the equation 9x plus 3y is equal to negative 21, I'm allowed to do things to this equation, so long as I do the same thing to both sides. So, what if I decided to add negative 1 to both sides? So I do plus negative 1, and I do plus negative 1. Now I've done the same thing to both sides, so I'm not doing anything illegal. However, this left side has x's and y's, so why do I want to introduce a constant to it? Well, I don't really want to. However, there is one thing that's nice. In the previous equation, we found out what negative 1 is equal to in terms of x's and y's. 2x minus 3y is equal to negative 1. So, I can take this 2x minus 3y and I could substitute it into this negative 1. This then becomes plus 2x minus 3y and plus negative 1. So, when I'm actually adding the two equations together, even though it looks like I'm adding things that are different to both sides, they're actually equal to each other. So I'm still doing the same thing to both sides. So it's a legal move and I'm allowed to do it. So let's actually add these together now. So I'm going to rewrite my system, and we have 9x plus 3y is equal to negative 21, and we had 2x minus 3y is equal to negative 1. So let's actually add these together. And now, easiest way to do it, just put a line and a plus sign. This then becomes 9x plus 2x is going to be 11x, and we have plus 3y and minus 3y. So I have a positive and a negative version of 3y. So when I add them together, I'm going to get 0y. And then we have negative 21 plus negative 1. That's going to be negative 22. Now 0y is just 0, so we have 11x is equal to negative 22. Dividing by 11, we have x is equal to negative 2. Now from here, I can take this x equals negative 2 and I can plug it into either one of these equations to figure out what y is. So I'm going to choose the top one because I think it looks easier. So we have 3x plus y is equal to negative 7, but x is equal to negative 2, so we'll have 3 times negative 2 plus y is equal to negative 7. This will be negative 6 plus y is equal to negative 7. I'm going to add 6 to both sides, and so we get y is equal to negative 1. So the solution to my system is going to be negative 2, negative 1. Now we should check that this actually works for both of our equations, so let's plug it in. Let's try the top one first. So we have 3 times negative 2 plus negative 1 is equal to negative 7. 3 times negative 2 is negative 6, and then plus negative 1 is equal to negative 7. So we have negative 7 is equal to negative 7. That's a true statement, so it works for this equation. Now we can try for the bottom equation. We have 2x minus 3y is equal to negative 1. So we have 2 times negative 2 minus 3 times negative 1 is equal to negative 1. 2 times negative 2 is negative 4. And negative 3 times negative 1 is positive 3 is equal to negative 1. Negative 4 plus 3 is negative 1. And so we have negative 1 is equal to negative 1. That's a true statement. So our answer really is negative 2, negative 1. Moving on to number 3, we can solve this system using either one of our methods. Now I'm going to use the substitution method for no rhyme or reason other than I want to practice using the substitution method. So let's look at both of these equations and see which one is easier to solve for. Now the top one has a bunch of fractions in it, so I don't think I want to use that one to solve, but the bottom one looks easy enough to solve for. Now if I want to solve for y, I'm going to have to divide by that 2 at some point, so I would just have to add more work to it. But if I want to solve for x, all I have to do is get it alone. So I'm going to solve for x. So rewriting, I have x plus 2y is equal to 4. And I'm going to solve for x. So I have x is equal to negative 2y plus 4. Now I can take this and substitute it into my top equation. So I have 5 halves times x, but x is equal to negative 2y plus 4, plus 9 halves times y, and all of that's equal to 8. Now, before I distribute everything out, I see that I have a denominator of 2 in both of these places. So I'm just going to multiply both sides by 2 to get rid of that, so I don't have to deal with any more fractions for the time being. So, multiplying both sides by 2, I'm going to have 5 times negative 2y plus 4 plus 9y is equal to 16. Distributing the 5, we have negative 10y plus 20 plus 9y is equal to 16. Now combining like terms, we have a negative 10y and a positive 9y, so that's going to turn into negative y plus 20 is equal to 16. Now I'm going to subtract the 20 over, and we have negative y is equal to negative 4, and hence y is equal to positive 4. Now I'm going to take this y equals 4 and I'm going to substitute it into either one of these equations, but the bottom one looks a little bit easier, so I'm going to use that one instead. So x plus 2 times 4 is equal to 4. So we have x plus 8 is equal to 4, and hence x is equal to negative 4. So my solution is negative 4, 4. But let's check both equations to make sure it satisfies both of them. So in red we have our top equation. So 5 halves times negative 4 plus 9 halves times positive 4 is equal to 8. Multiplying that out, we're going to have negative 20 over 2 plus 36 over 2 is equal to 8. Now negative 20 over 2 is going to be negative 10, and 36 over 2 is going to be 18. And so we have negative 10 plus 18, which is positive 8, is equal to positive 8. So that is a true statement. So it works out for the first equation. Now let's try the second equation. We have negative 4 plus 2 times positive 4 is equal to 4. Now negative 4 plus 2 times 4 is 8 is equal to 4. Negative 4 plus 8 is positive 4, and so we have 4 is equal to 4. That is a true statement. So our answer really is negative 4, 4. Moving on to number 4, we have another system of equations, and I'm going to use the substitution method just for the sake of practicing it. Now, neither of these equations are jumping out at me as to which one I should use, so I'm just going to pick one of them. So I'm going to choose the bottom one. So we have 5x minus 4y is equal to negative 30. Now I'm going to solve for one of my variables. So I have a positive 5x and a minus 4y, so I'm just going to add 4y to both sides. So we have 5x is equal to 4y minus 30. Now I'll divide by 5 and we get x is equal to 4/5 y minus 30 divided by 5 is 6. So now I can take this and I can substitute it into the other equation. And so we have 2 times 4/5 y minus 6 plus 3y is equal to 11. Distributing this out, we have 8/5 y minus 12 plus 3y is equal to 11. Now I'm going to add the 12 over, so we're going to have 8/5 y plus 3y is equal to 23. Now I have this denominator of 5, and I'm going to get rid of that by multiplying both sides by 5. So we'll have 8y plus 3 times 5, which is 15y, is equal to 23 times 5, which will be 115. Now 8y plus 15y is 23y. And so we have 23y is equal to 115. So now we can actually solve for y. So dividing both sides by 23, we have y is equal to 5. We can take this and plug it into one of our equations to solve for x. So I'm going to choose the first one since it has smaller numbers. So we have 2x plus 3 times y, which is 5, is equal to 11. So we have 2x plus 3 times y, which is 5, is equal to 11. So 2x plus 15 is equal to 11. Subtract the 15 over, and we'll have 2x is equal to negative 4, and hence x is equal to negative 2. So our solution is negative 2, 5. Now it's always good to check our solution on both of our equations, so let's go ahead and do that. So in red we have the top equation, 2 times negative 2 plus 3 times 5 is equal to 11. So 2 times negative 2 is negative 4 plus 15 is equal to 11. Negative 4 plus 15 is 11, so we have 11 is equal to 11. That's a true statement. Now our bottom equation, we have 5 times negative 2 minus 4 times 5 is equal to negative 30. So we have negative 10 minus 20 is equal to negative 30. Negative 10 minus 20 is going to be negative 30, and hence negative 30 is equal to negative 30. That is a true statement, so our solution really is a solution. Moving on to number 5, we have another system of equations, and this time I'm going to use the addition method, again, just for the sake of practicing a different method. So I want to try and get opposite coefficients. Now I think turning a 12 into a decimal is going to be harder than turning this decimal into an integer. So I'm going to multiply my top equation by a number to try and get it equal to 12. So let's rewrite it. 0.2x minus 0.3y is equal to 2, and 12x minus 18y is equal to 5. Now I want to multiply both sides of my top equation by some number to turn that 0.2 into a negative 12, right? Because I want the same coefficient but opposite sign. So how do I turn a 0.2 into a 12? Well, I can kind of do it in steps. How do I turn 0.2 into 1? Well, I multiply it by 5. And then how do I turn a 1 into a 12? Well, I multiply it by 12. So I multiply by 5 and by 12. So really I'm multiplying by 60. But I want it to be the opposite sign, so I'll do negative 60. So this becomes negative 12x, and then negative 0.3 times negative 60 is actually positive 18. So plus 18y is equal to negative 120. Then we have our other equation still, 12x minus 18y is equal to 5. So when doing the addition method, once you have your opposite signs, you just put a line under and add both sides together. So let's go ahead and do that. So we have negative 12x plus positive 12x. So those are going to cancel each other out. So we have 0x. Now we have plus 18y minus 18y. So those are going to cancel each other out. So we have 0y. And then all of that is going to be equal to negative 120 plus 5, so negative 115. So what do we have? We have 0 is equal to negative 115. Is this a true statement? Well, no, right? 0 is not equal to anything other than 0. Something is wrong here. So let's go ahead and check out the equation right above it. So we have 0x plus 0y is equal to negative 115. What happens if I choose a value for x or a value for y? Well, I'm multiplying it by 0. So, is there any combination of x's and y's that I can plug in here to get it to be equal to negative 115? Well, no, it doesn't matter, right? If I choose a billion for x, I'm still multiplying it by 0. So it's going to be equal to 0. And the same thing goes for y. If I plug in a billion there, it's still going to be 0 times that number. And so we're always going to have 0 is equal to negative 115. It doesn't matter what I choose for x and y. I'm always going to end up with this false statement. Since this is the case, it turns out that there's actually no solution. As in, there's no combination of x and y that I can plug into both of these equations in my system to have them be true at the same time. Now, we can take a little bit of a deeper look at this. When we go back to here, we can kind of see something. Our x's and y's both canceled out. Let's go ahead and rewrite it. We have negative 12x plus 18y is equal to negative 120, and we have positive 12x minus 18y is equal to 5. Well, if we look at our left side right here, they have the same coefficients, but they're just opposite. So I'm going to multiply one of these equations by negative 1 so they have the same coefficients. So if I multiply the top equation by negative 1, we're going to have positive 12x minus 18y is equal to positive 120. And then we rewrite our second equation, 12x minus 18y is equal to 5. So really, what is this saying? I'm saying something is equal to 120, and then I say the same thing has to be equal to something different. I'm saying 12x minus 18y is equal to two different numbers at the same time. Well, that just can't be true. It can only be equal to one thing. So this is where our inconsistency comes from. This is why there's no solution. Moving on to number 6, we're going to use the addition method for the sake of practicing it. So, immediately I see a positive 1 and a negative 4. Anytime you see a positive 1, it's usually really easy to set it up because all you have to do is multiply by the other coefficient. So, I'm going to try and eliminate our y's. So I'm going to rewrite our equations. Negative 3x plus y is equal to 2. And then I have 12x minus 4y is equal to negative 8. Now I'm going to try to eliminate my y's, so I want them to have opposite coefficients. So I'm going to multiply this whole top equation by positive 4. So we get negative 12x plus 4y is equal to 8. Writing our other equation, we have 12x minus 4y is equal to negative 8. So let's go ahead and add these together. So we have negative 12x plus 12x, so we get 0x. And then we have positive 4y and negative 4y, so we get 0y. And we have positive 8 and negative 8, so we get 0. So we have 0x plus 0y is equal to 0. This is just known as 0 equals 0. Now, 0 is equal to 0. That is a true statement, but something seems a little odd. Let's go back and check out our previous step real quick. We have 0x plus 0y is equal to 0. Now, what happens if I choose a value for x and a value for y? If I choose 5 to be x and 10 to be y, what's going to happen? I'm going to multiply it by 0, and I'm going to multiply the other one by 0. So, no matter what I choose for x and y, I'm always multiplying it by 0. It doesn't actually matter what values I choose for x. I could choose 1 billion for x and 1 trillion for y, but because they're both being multiplied by 0, I'm always going to end up with 0 equals 0. So it turns out that there's more than one solution. There's actually infinite solutions. Let's take a closer look like we did the last time. So we have negative 12x plus 4y is equal to 8, and we have 12x minus 4y is equal to negative 8. Now, both my x's and y's canceled, so they had opposite coefficients. So I'm going to multiply one of the equations by negative 1 to make sure they have the same coefficients so we can look at it a little bit better. So I'm going to multiply the top one by negative 1. We're going to have 12x minus 4y is equal to negative 8. And then our bottom equation was 12x minus 4y is equal to negative 8. So what do we have here? Our system of equations is really a system of two of the same equations. So when we have two of the same equations, it turns out I have infinitely many solutions. Now, how do I actually represent infinite solutions? Well, we have an equation here, 12x minus 4y is equal to negative 8. How do we normally represent an equation? We get it to look like y equals stuff. So let's do that here. So I have 12x minus 4y is equal to negative 8. Now I'm going to get y equals stuff. So I'm going to subtract 12x over. So I'll have negative 4y is equal to negative 12x minus 8. Now I'm going to divide by negative 4. So we have y is equal to 3x plus 2. So this equation that I have in my system is really the equation of a line with slope 3 and y-intercept of positive 2. So it turns out any point along that line is actually a solution to my system of equations. So I can represent this in set builder notation as the set of all x and y such that y is equal to 3x plus 2. Now, don't be intimidated by this. This looks scarier than it is. All this is saying is that my answers are going to look like a point, x, y, but there's a condition involved. That condition is saying that y has to be equal to 3x plus 2. As in, this point has to be on this line. If the point is on this line, then it satisfies my system of equations. So, set builder notation is just saying my answer looks like this. This bar is saying that there's a condition involved, and that condition is on the right side. It has to be on this line. So, that's our solution to number 6. That's going to do it for this video, and I hope to see you in the next one.